Hope you're all having a good day. My name is Hector. I'm going to go over question 56. So if a car stops suddenly, you feel thrown forward. We like to understand what happens to the passenger as a car stops. Imagine yourself sitting on a very slippery bench inside a car. This bench has no friction, no seat back, and there's nothing for you to hold on to. And we're just going to go through these diagrams. So first off, draw a picture and identify all the forces acting on you as the car travels at a perfectly steady speed on the level ground. So kind of just scrolling down here. This is the diagram. So we want him to be traveling at a steady speed, so there's no net force, there's no acceleration for this guy. So the forces in the x will cancel out, and the forces in the y will cancel out, and that is the normal force and the gravitational force that will cancel in the y. And we know there's no friction. Well, I assume there's no friction because the bench is very slippery, so I assume friction is negligible for this situation. And this will get us our man going at a constant velocity. Yes. Going on to B, so this is draw a free body diagram. This is this is no net force. Trying to read my handwriting. No net force. Everything cancels. He shouldn't be accelerating. He's not accelerating. If we kind of go back here and make this a bit more realistic, we can kind of think of this as having some static friction. But because we're told the bench is very slippery, we're going to basically, I'm pretty sure we're going to ignore static friction and the force pushing the car forward. And then going into part C, so this repeats part A and B with the car slowing down. And this is C, so if the car is slowing down, the person is not slowing down. So this is why the bench is very slippery. There's no friction force pushing him with the car. Nothing keeping him to his seat. So he's going to simply slide off his seat. This is Newton's first law. So we have two objects to look at. We have the car and we have the man. So if the car slows down, right, there's a force enacting there, the force of the brakes. However, because the man inside the car is on a very slippery bench, there's no friction, no internal force keeping him from moving. He's an object in motion. He will stay in motion until he hits the front of the car. And so this is part C of the question. Part D, yeah. So as the car slows down, right, the guy will just simply fly off his seat into the front, which is why friction is so great for us real people, because it keeps us from doing exactly that. And again, you kind of see over here, I've kind of listed like, the x's will cancel and the y's will cancel. The person's forces and the car's forces will be totally different, and that's why he'll fly off. Again, Newton's first law in the class. And then going on, we have parts E. So Newton's law to explain why he's being thrown forward as the car stops. So we kind of already did that. I'm kind of going a little ahead of here, I guess. Newton's first law states that an object in motion will stay in motion, and an object at rest will try to stay at rest. It's his first law, and so you seem to be thrown forward because you're an object in motion, right? Just like the car. And though the car has a force enacting on it, there's different forces that make you, slow down. So actually, there's different internal forces like friction and like your seatbelt and all these different forces. But initially, before those forces start enacting on you, you continue to move forward after the car starts to slow down for a very short amount of time. So you feel very thrown forward in your seat. So what if the bench is not slippery and the car slows down? You stay on the bench and don't slide off, obviously, but what force is responsible for that deceleration? What direction does it point? So we're going to go ahead and go all the way down to the very bottom of my little list. Again, this is just a second statement of Newton's first law, and kind of just looking at this one. So you're going to have, I guess it would be static, actually, if you don't move. So we're going to go ahead and change all these sub K's to sub S's. It would be sub K if you were in motion, but because the question said we're not in motion, we can just go ahead and write this is static, right? And so when the car slows down, what slows you down is that friction force, the friction of your seat. It makes you stop from being thrown actually out of your seat. You're just kind of thrown forward, and then you're kind of kept in your seat. And you can kind of see this in the units, right? So, and this F net, you decelerate. So that's why the F net is pointing in the left direction, because you have some if you imagine the system as the car, right? Then car slowing down, so internally the internal forces, or if you imagine you as a system, then you'll be slowing down, and that's the static friction that's accounting for that, which is why you don't move, you're not moving, so it just stops. It basically stops you in your spot. So I don't know if it would be right to call it F net actually, but it is technically the net force in the X direction. You're just not really, you are accelerating. It's yeah. And then if you were to have a seatbelt on, it would be obviously the force of the belt on you and the force of the friction that would add up and keep you from flying off your seat from that, from Newton's first law that wants to keep you going forward. So that force has to be applied to stop Newton's first law. So obviously this is an ideal situation. So I have a little graph here just for a little bit of context of like what it actually means to decelerate in a car. These are some braking graphs. So this is someone's braking up to a stoplight, and you can kind of see that it's not a straight line. Like, who would have thought, right? And so you can imagine if you were to have, again, this should be a static friction force. If it was kinetic, you would be flying off your seat. You would be sliding on your seat, technically. And you can imagine that as these different accelerations kind of go through, you would have different forces pushing on you, pulling on you, and your friction force would compensate, which is why when you're driving in a car, you go up to a stoplight and you're, the driver's kind of braking and off braking and braking and off braking, you don't get thrown out of your seat. So yeah, just really relating this to Newton's first law is like really the most important thing is that object in motion wants to stay in motion, so you need some force to stop it or to change its direction or change its magnitude. And yeah, I think that's really just the question. I hope y'all have a good day. Bye.